everyone. In the previous lecture, we had discussed about an overview of an operating system. In today's lecture, we will be seeing about processes and threads. Now let us see what a process is. A process is a program in execution. That is, it is an instance of a program which is running in the computer. For example, if you want to take a printout, or you want to perform some calculations in the Excel sheet, or you want to type some Word document, all these things are programs, and these when running is called as a process. Now let us see what a PCB or a process control block is. A process control block contains all the information as regard to a process. There are many components as far as a process control block is concerned. The first component is an identifier. Based on each process, a unique identifier is being given. This is for identification purpose of each process uniquely. Okay, so this is the first component in a PCB. The next component is the priority. So each process has a particular priority as compared to the other processes. So this is also stored in the PCB. The next component is the program counter. A program counter is a counter which contains the address of the instruction to be next executed by the process. This is also stored in the PCB. Next component is the process state. That is, a process can be in different states. For example, it can be ready, it may be running, it may be suspended, or it may be blocked. So, the state in which the process is stored in the process state of the PCB. Some other components include memory pointers. Memory pointers are pointers to page table or segmentation table based on the structure of the memory. It contains pointers to various registers of the process. The next component is the context data. That is, whenever a process is preempted, all the data of the process has to be stored somewhere. All these data are stored in the context data, and then it can be used for later restarting of the process. And then we have the accounting information. In this, all the accounting information of the process, for example the time limit, the CPU usage and so on, are stored in the accounting information of the PCB. And finally we have the IO status information, that is whether some IO devices, that is input and output devices, are called and what is the status. All those things are stored in the IO status of the PCB. Now let's see when a process is created. A process can be created in two ways. One is system initialization and second is system call. So what is system initialization? Whenever an operating system starts or get initialized, then one or two processes get started or it gets created. This is called as system initialization. The second one is system call. That is, whenever we call for creating of a new process, then it is called as a system call. The system call can be executed in two ways. Either a user can call for a new process. In this case, a system call is called for creation of a new process and a new process is created, or else from already running user data or already running system daemons, a new process can be created. In such cases, the already running user program or the system daemon will call for a new process and the new process will be created. Now let us discuss about process creation. In process creation, we will be discussing about parent process and children process. A parent process will be creating multiple children process. In this case, each children process will in turn create their own children process, and so on. A tree will be created. Each process will be uniquely identified using the PID or the process ID, which is stored in the PCB or process control block. The various resource sharing option is that 1. The parent process and the child process can together share all the resources or data, or then the child process will share a subset of the parent process resources, or then the child process and the parent process won't share any resources at all. Similarly, as far as the execution is concerned, the parent process can wait till the child process finishes its processing, or else the parent process and the child process can concurrently perform the execution. Now let us see how a process terminates or ends. A process can terminate or end based on two conditions. One is voluntarily and second one is involuntarily. A process can terminate voluntarily whenever it terminates on its own knowledge, and whenever a process is terminated forcefully, it is called as involuntary termination. Voluntary termination can be of two types. One is normal exit and another one is error exit. Whenever a process is executed and the execution is completed, then the process is voluntarily exiting or terminating. This is called as normal exit. Whenever an error occurs when the process is getting executed, this is called as error exit. As far as involuntary termination is concerned, it means that the process is terminated involuntarily or without its knowledge or forcefully. In this case, there can be of two types. First one is fatal error. That is, whenever a process is taking place and a fatal error occurs, then the process is terminated involuntarily. Similarly, in case if the process is killed by another process, then also this process is terminated involuntarily. Now let us see the concept of process hierarchy. Whenever a process wants to create a clone of itself, then it can do so using the fork system call. In such case, a clone of the whole process is formed and the process is created such that a PCB or a process control block is created for the new process, a separate memory is allocated for the new process. So this is called as the child of the previous process. So here comes the parent-child concept. In this case, the child can by itself create new children. So this is called as process hierarchy. Unix has the concept of process hierarchy. In such case, it is called as process group. Windows does not have the concept of process hierarchy. There, all the processes are created equally. A process can be in various states based on what it is being performing at that particular time. For example, it can be either created, ready, running, blocked or exit. Now let us see each of these states in detail. The first state is created. Whenever a new process is created, a particular memory is allotted for that process and moreover PCB or process control block is created for that process. This is called as created state of the process. Whenever the process is given for execution, then it is given to the queue. This is called as the ready state. And whenever a process is taken by the scheduler from the queue and it is being executed, it is called as the running state. Whenever a process is preempted or when we want an event to be occurred, then we will go to the block state. That is, whenever a process wants the printer or it wants a scanner or a keyboard, then it will go to the block state, wait till that particular resource is free and then it will come back to the ready or the running state. And finally, when the whole process is executed, it will go to the exit state. The structure of a process in an operating system is discussed here. The structure of a process in an operating system consists of two layers. The lowermost layer consists of the operating system which performs interrupt handling, scheduling and so on, while the upper layer consists of processes in a sequential manner. Each processes are tracked using process table. Each process has a separate process table entry. Now that we have seen various concepts about process, let us see what a thread is. A thread is a path of execution within a process. A process may have multiple threads. Now let us see why we need a thread. A thread can also be called as a lightweight process. The idea behind implementing a thread is that multiple tasks can be divided from a single process and parallelism can be created. For example, in case of a browser, we will be having multiple tabs. All these tabs can be considered as different threads. Similarly, in case of MS Word, we will be having different threads for formatting the text, for processing the input and so on. Now let us give a real-time example of what a thread is. For example, if you want to transfer a pen from the right side of the hand to left side of a hand, there are two options. Either we can create a clone of myself, which is also a process. In such case, what happens? There will be extra memory, extra overhead and that person will transfer the pen from right of my hand to the left of the hand. Another solution is to create a clone of my hand. In such case, the hand will transfer the pen from the right of my hand to left of my hand. In such case, the overhead is reduced and memory is also reduced. This is an example of thread. Now let us see some of the basic difference between the process and the threads. We all know that multiple threads are present in the same process. So when execution of multiple threads takes place, they take place within the same memory space, while execution of different process takes place in different memory space. This is the primary difference between the process and the thread. Another difference between the process and thread is that unlike process, threads are dependent on each other. As a result, the code section, data section and the operating system resources are shared between different threads among the same process. But like a process, the thread also has its own program counter, register set and stack. Now let us see some of the advantages of threads over processes. The first advantage of thread over process is responsiveness. When a single process is divided into multiple threads and if a single thread finishes the execution earlier, then this output can be returned immediately and as a result the responsiveness can be increased. The next advantage of threads over processes is faster context switching. That is, the context switching of threads is far more lower as compared to the processes. Moreover, the overhead of context switching in CPU of the process is higher as compared to the threads. So, as far as thread is concerned, there is a faster context switching as compared to the process. The next advantage is effective utilization of multiprocessor system. That is, when a single processor is being able to process multiple threads, then a multiple process system will be definitely able to schedule better jobs and as a result effective utilization of multiprocessor system is possible. The next advantage is that of sharing of resources. Sharing of various resources like codes, data and files can be done within the threads of the same process. Next comes the communication. Communication among different threads in the same process is quite easy because all of them have the same address location. As compared to various processes, communication among various processes is difficult and needs a specific method. The next advantage of threads over process is that of better throughput. That is, when a process is divided into multiple threads and each thread is given a job, then the number of jobs given at a time is increased and as a result the throughput is increased as compared to the process. Now that we have seen differentiation between processes and threads, let us see various categories of threads. Threads can be categorized into two types. One is user level threads and another is kernel level threads. User level thread, as the name suggests, is created by the user applications. That is, it will be created by the user application and it will also be managed by the user libraries. And the kernel level thread, as the name suggests, kernel is the integral part of the operating system. So the kernel level thread is also created and managed by the operating system. User level thread is faster in execution as compared to the kernel level thread. Now let us see various multi-threading models. Multi-threading models can be of three types. The first one is many to one. That is, many user level threads are connected to single kernel level thread. This is quite commonly used. Then the other type of model is one to one. That is, one user level thread is connected to one kernel level thread. One example is of Windows. And then the last one is many to many. That is, many user level thread is connected to many kernel level thread. It is quite complicated and the benefits are quite less. So it is fairly used. Thus we have come to the end of the session. In this session we have seen about processes and threads. Hope you all understood about it. In the coming session we will be discussing about concurrency and deadlock management. Thank you.